We left off with this example. We classified each of the different numbers. Square root of 5, for instance, was irrational and real. Square root of 81 was really just the number 9. So it was natural, an integer, rational, and real. We applied all of those labels to it. So good problem. And so we can just remember what the basic sets and subsets look like, what falls into what category, and so on. And you can see here's just some of the answers that we just went through ourselves. So the real numbers, remember, the real numbers are basically all the numbers that we could possibly care about, especially for this course. The only thing that gets you away from being a real number is if you try to use some weird constant called I. But if you're not trying to do that, then you must have a real number, most likely. What we have is we have a couple of different properties, a couple of different rules that are true about the real numbers, and they create a lot of interesting mathematical concepts that we should pay attention to. Some of the big ones, the closure property of addition simply says if I add any two real numbers, the result is a real number. That shouldn't be horribly surprising, but it is nice to know that that's true. There's also a closure property for multiplication. If I multiply any two real numbers, I'm going to add up one, or I'm going to end up with a real number itself. So the product, there's a product rule basically for closure. Now here's where we get into some of the interesting ones. Those first two you could have probably figured out, but this one, the commutative property. The commutative property, it's for both addition and multiplication. And it says that if I change the order of addition, it doesn't change the final result. You're still going to end up with the same thing at the end of the day. So A plus B is equal to B plus A. 13 plus 7 is the same as 7 plus 13. Same thing for multiplication. If I multiply the other way, if I do 13 times 7, it's the same as 7 times 13. Doesn't matter which way you do it. Not every operation for every set of numbers has these kinds of closure properties, but the real numbers certainly do. Oops. The real numbers certainly do. So there's a commutative property for addition. You think, why do they use the word commutative? Well, you think about if you were a commuter, that means you're traveling somewhere, you're moving about, and that's what you're doing with those numbers. You're changing their order, you're moving them around with each other in relationship to each other. Now, would you guys say that there is a commutative property of subtraction? No, absolutely not. If you reorder the way you subtract, 13 minus 7 is not the same as 7 minus 13. So reordering numbers in subtraction is not quite commutative. However, if you express subtraction as just adding of the negative, then you're talking about addition, and you can commute addition as long as you keep that negative sign. So, you know, it's almost semantics in a way. Would you say there's a commutative property for division? No. If you do 3, or if you do 9 divided by 3, that's not the same as if you flip them and do 3 divided by 9. They're going to give you two completely different answers. So it's important to note that. Yada, yada. There's some other properties. We're not going to necessarily care so much about all of these. It's not like we're going to weep any tears if we don't see some of these again, but others of them are incredibly useful, and we are going to manipulate them and utilize them as much as we can. So the associative property, it just tells you that you can group things differently. See where the parentheses are? Here the parentheses are around, so let's say you're doing A plus B plus C. If you put the parentheses around, stop doing that. You're bad. There we go. If you put the parentheses around A plus B first, and it wouldn't matter if you actually did B plus C first. No matter how you rearrange and regroup terms, it doesn't matter in addition. Same thing for multiplication. Why do we care so much about the associative property? Look, if I'm leveling with you, if I'm being completely straight with you, you probably won't see a lot of use for the associative property in this course. What the associative property is really useful for in mathematics is that it proves other properties that are useful. So this just kind of forms a basic building block that you might care about for other mathematical properties. Now here's the one we really care about. Well, that's as much as I can zoom in. Here's the one we really care about. That beautiful, wonderful distributive property of multiplication over addition. What that means is that if I'm adding two numbers, but outside I'm multiplying some other number into the mix, that number I'm multiplying in distributes. A goes to the B, A goes to the C, and then I multiply first. I do A times B plus A times C. And so the distributive property all of a sudden has a lot of wonderful applications. So here's an example, 7 times, and then you do 4 plus square root 3 in parentheses. They have a, this is one way to look at it, one example. But the distributive property is so much more important than that example. That example is almost silly, like it demonstrates that it works. The distributive property has so many other wonderful uses. And I know what you were thinking. You were thinking over the weekend, you're like, oh gosh, I can't wait to get to my math class on Monday morning. I think Mr. Gunther is going to teach us about different properties of real numbers. That's more interesting than the AFC or NFC championship games that were yesterday. Tom Brady is going to another Super Bowl, the first year with a brand new team. I mean, come on, this guy is just good. You want to hate him, but you just can't. He's just a winner. Anyways, let's look at some interesting applications of the distributive property. What if you had to do, I don't know, 7 times 83? You had to do 7 times 83 with a twist. What if for some reason you had to do that in your head? What if you were buying 7 objects that cost $83 a pop or something like that? And your phone is off or it's not working. What if you just want to do a quick mental math? You can do it in 10, 15 seconds maybe with this cute little trick. If you had to do 7 times 83 quickly, you could rewrite 83 as 80 plus 3. Would everyone agree that 83 is 80 plus 3? Anyone disagree? Any nays? So you're doing 7 times this thing. We're putting it in parentheses because we know that the 7 has to really multiply to this whole number just like it was multiplying to the whole number over here. But now the distributive property lets me do something like this. I can call that 7 times 80 plus 7 times 3. Well, 7 times 8 is 56, so 7 times 80 must be 560. 7 times 3 is 21. So we're going to end up with, what is that, 581. So some of you might do that in your head. If you were to do 7 times 83 in your head, you might do, okay, 7 times 80, and then you might also go do 7 times 3 and just add those numbers together. You've probably done that computation real quick in your head, and you maybe not even realized that what you were doing was just the distributive property, was just the distributive property. So the distributive property gives you some nice, clear ways to estimate multiplication, estimate some numbers. Another idea, another thought to think about. Be ye very careful that there are parentheses in order for the distributive property to apply. Here, this is just 17 times 4, whatever that comes out to, and then add it to the number 9. So that's one thing. If I put parentheses around the 4 plus 9, then that's a different thing. Then I'm distributing the 17 to both the 4 and the 9. So just be careful that you know where the parentheses are. The parentheses basically tell you that everything in here gets that 17. Everybody gets a piece of 17. You drop the parentheses, get out of here. You just have that. You don't multiply the 17 to the 9 in that case. Finally, the distributive property is basically the reverse of factoring. We're going to get into some factoring that involves variables and coefficients, things like that. We're going to get into that a little bit later on in the semester, maybe here just in a couple of weeks. So the distributive property is nice because it's like going the opposite way of what factoring would try to do. For instance, we're going to see that something like (6x squared minus 9x). And you don't necessarily have to know how to do this right now. We're just kind of peering ahead into the future. You'll find out that you can actually factor out the greatest common factor. And so we actually went the opposite way of distributing. Here, we would do this 3x, we would think to distribute it in here. But what we actually did was we wanted it to look like this. So it's just all about context. Sometimes you want to distribute, depending on what you're doing. Sometimes you want to undistribute, you want to undo distributing, which is just our way of factoring. And it just depends on when you need to do what. What is your underlying goal? So lots of properties. The identity property of addition just says adding 0 to something leaves it unchanged. It's the identity, meaning it maintains the original identity of the number you're starting with. Adding 0 does not change the value. It retains the identity. Of course, you probably already knew that. You add 0 to something, you're not adding anything into the mix, so it doesn't change anything. Well, there is already an identity property of multiplication as well. For addition, if I add 0, nothing changes. For multiplication, if I multiply by 1, it doesn't do anything. Multiplying by 1 retains the original number. So some pretty useful, important properties again. Allow me to sneeze for one moment. Nope, it left. Sometimes you got to catch a sneeze before it just won't go. It's not in your nose anymore. It's gone. Your window of opportunity was very slim. And in that case, it was very, very slim. So, anywho, multiplying by 1 does nothing. I want to say, maybe it's 9 o'clock in the morning. They're just not super receptive to humor just yet. They haven't had their coffee. But I think I just have to accept the difficult truth is that I hit my peak funny in my early 20s. Early 20s, I was, everyone was like, ha ha, Josh. Or maybe they were just pretending. They were just like, well, he's a nice guy. We don't want to hurt his feelings and tell him he's not funny, but he's painfully unfunny. I don't want to watch this guy for any more than I have to. And I think that's what's going through a lot of your minds right now. So I'm going to stop doing humor, okay? No more. I'm just going to come up here and I'm just going to cite this stuff robotically as I can. How many of you want that? How many of you want that? How many of you, while you may not find me humorous, how many of you like that I at least attempt humor? That it kind of makes this thing, you like that, okay. I think my heart just grew 2 sizes all of a sudden. Anyways, so Idel, I see some smiles. I see some masks slowly lift up 1/2 inch. That means you're smiling. So anyways, and out in the Zoomosphere, I hope you're smiling as well, because you know what, if you can't smile about math, well, math usually doesn't give us a lot of reasons to smile, I suppose, but maybe we can. Inverse property of addition. What an exciting thing. Inverse property, what does it mean? What the inverse property will do is it allows us to go from one number and get us to the identity for whatever that operation is. In the case of addition, the identity operator of addition is 0. So what we want to do is we want to start with any number and be able to get it to 0. What do I have to add to it to get it to 0? And what you have to do is you have to add to it the negative of it, whatever its opposite sign number is, but it otherwise has the same absolute value. So if you have square root of 3, you want to add a number to it to get it to 0, add negative square root 3. If you have negative pi and you want to add a number to it to get it to 0, add pi, positive pi, and you'll get it to 0. These may not look interesting right now. You might be bored out your mind. You might be thinking this isn't super important. Where these two properties here, inverse properties, are going to come up is when it's time to solve equations. And you better believe we're going to be solving some equations very soon. Very soon it will happen. And so what we're going to care about is when we solve equations, sometimes you got to move things to the other side of the equation in order to get the variable by itself. And in order to do that, you have to add the inverse, or you have to multiply by the inverse, something like that. And that will help you isolate your variable. So same thing here with, there's an inverse property of multiplication. Now, instead of we want to multiply by a value to get it to 0, now we want to multiply by a value to get it to 1, to uno, which again is the identity property for multiplication. So if you have some number a, you multiply it by its reciprocal, 1 over that value. And we've talked about the reciprocal already. So for instance, square root of 3, you got to multiply by 1 over square root of 3. 17, if you want to get 17 down to 1, you want to multiply it by something. You do 17 times 1 over 17. You multiply by its reciprocal. Again, doesn't sound interesting, but this is how we can solve equations. That's what we're trying to get to. Equation solving. So bada bing, bada boom. You do square root of 3 times 7, or if you do 7 times the square root of 3, you're changing the order. You're using the commutative property here. It's kind of warm in this room. Is anyone else warm? I'm a little warm. Okay, we might change the air conditioning in a little bit. How many, is anyone cold? Is there anyone who's cold in the room? It's okay to speak up and say if you're cold. There will be no judging. Okay, so maybe we do need to make it a little less cold in here. What an American problem to have. It's too warm in a room when it's cold outside. Yeah, well, that's a very first world problem, I think. But that doesn't mean just because it's a first world problem doesn't mean you shouldn't try to fix that problem. Doesn't mean you should just let it go. Anywho, if you regroup addition like that, 4 plus 7, you do that first and then you add 6. That's the same as if you were to do the 7 plus 6 first, add 4. Here, if you distribute this 2, that's the distributive property. If you add negative 17 onto 17 and it gets you to 0, get out of here. That's the inverse property of addition. Now, this clockwise addition stuff, we're not going to go super into it. They introduce a different kind of addition. It is interesting if you go further down the rabbit hole with math, but we're not going to do that. So let us not get into the weeds with it. All right, let me queue up. This is fun. We're just having fun. All righty. Now we're finally ready to bust out into chapter 6. Chapter 6, yay, everyone. I want everyone in the room, don't say it out loud, but in your head, I want you to say yay. How many of you tried to resist saying yay in your head? Be honest. How many of you tried to resist? Maybe you did a little bit, but how many of you, by trying to resist, you couldn't help it, right? You couldn't help it, you still said yay in your head. That's actually a really interesting psychological phenomenon where you tell a bunch of people not to think about something, but the fact that you just told them that, they're going to think about it. It's impossible for them not to think about it. And you can actually use that kind of things to manipulate people. Now, I don't believe in manipulating people. I think it's wrong. I believe very much that you have a free will, and you ought to be able to use that free will to go get Dairy Queen at 11 p.m. at night. Have I done that recently? Maybe I have. Don't judge me. Well, so there's one that's open at 11. Yeah, I know what you're thinking. Okay, better example, Whataburger at 2 a.m. Okay, I've done that recently, absolutely. And when Walmart used to be open, would I go get some Twizzlers at 3 in the morning at Walmart? Yeah, but now they're closed at like 10 anymore because of, I guess there's this major pandemic going down, so that will change the hours of things. Anywho, so we're finally ready to talk about algebraic expressions and formula. And this is where people often will freeze up and they'll get scared or they'll be nervous or worried. And I say, don't be worried. We're all here. We're all in this together. It's okay. Algebraic expressions is just going to be us taking numbers or taking things that are meant to represent numbers, and we use variables, which are usually just letters of the alphabet, and we use them to represent those numbers. The idea behind it is that there are some problems that you're going to have to face in math, some problems you're going to have to try to solve, where there is something you don't know. In fact, that's what a problem is. There's at least one thing you don't know, and you're trying to deduce it from the information you have available. We're going to use a variable to represent what we don't know. We're going to take the information from that problem, usually to build an equation around it, and if we solve for that variable, that's our way of deducing what we don't know. Now, there are some problems, math problems you can do in your head, and you might think you're not using the same reasoning, but you're using the exact same reasoning. We're just formalizing what it means for to have an unknown. But we got to use algebraic expressions. So algebra is actually really interesting. Most of you may have taken algebra in high school. You had algebra 1 and you had algebra 2. And then you said, hey, once you finish algebra 2, I'm done with algebra. Well, you might personally be done with it. That's true. It turns out algebra is a major field in mathematics. It's still very large to this day. There are still people getting their PhDs in mathematics at huge mathematics universities that are really well known for it, who are studying algebra to this day. And it's insanely complex. I've looked at some of the stuff. I sat in on friends who did their thesis on algebra stuff. And I was like, I don't know what this is. And I was a trained mathematician and I didn't know what it was. It's because algebra wasn't my field exactly. So what we're going to see here is considered the most introductory algebraic concepts, but it is really interesting to know that it goes way, way down the rabbit hole. So algebra uses letters, usually English letters. We call them variables. They're variables because they could change. When something varies, you're saying it changes from one place to the next. So the idea is it's a value that is not held constant. It is a value we don't know that could take on a number of values that we're trying to figure out which one it is. So it's a variable. A constant is a number you know. It's a number you know that's hard, it's set, and it ain't nothing else. So you might use X and Y. You can use any letter of the alphabet, except you probably shouldn't use an E, especially a lowercase e, because we looked at that. E is a constant in mathematics. It's a very important one. It's a value of about 2.718. So we'll just kind of talk about it real quick. E, just like pi, we've talked about pi, is about 3.144, excuse me. And it's irrational, so it's going to keep rolling without repeating any pattern. That's what pi is. We also have a mathematical constant called E, sometimes called Euler's constant, sometimes called Napier's constant. And E is actually probably more important than pi in mathematics. It's just you're not always going to have a reason to deal with it. We'll deal with E when we get to the Math 1332 portion of this course, when we talk about something called continuously compounding interest. So in other words, E is a constant in math, so we probably shouldn't use lowercase e as a variable. We should leave that one alone. Same with I. I is the complex coefficient, if you will. So we should probably leave that one alone. So lowercase e, lowercase I, we usually leave those out. We usually say, no, leave those alone. But X, I'm going to give it to you. Y, Z, You can use A, B, C, D, F, G, H, J, K, but E and I leave them alone. You might also see Greek letters, and I'm really bad at drawing Greek letters. You might see alpha. You won't really see a lot of beta. You might see theta. You might see sigma. You take a statistics course. So we could use Greek letters. We probably won't use them a lot in here, but it's just good to know. You can really use any symbol you want to represent a variable. Letters are just awfully convenient. Don't use a number to represent a variable. A 3 should be the number 3, not this 3 is actually a symbol for some number we don't know. That's silly. Don't do that. Now, an algebraic expression is we'll just read the definition straight up, is a combination of variables, numbers, and we can also throw into the mix, we can add them together, subtract them, we can multiply them together, we can divide one over the other. We can also use powers, exponents, if you will. X squared is x to the second power. You can use roots, square root of x, cubed root of x, 17th root of x, if you want to. That's pretty much all we'll ever really use. So that's good to know. So here's some examples. X plus 6, whatever x is, whatever this unknown value is, we're adding 6 onto it. Here we're squaring it and subtracting 6. Here we're saying 6x, which is our way of saying 6 times x. You have 6 of those x things, whatever they are. That 6, we're going to call it a coefficient. A coefficient, and it's implied to be multiplying. If you have just x plus 6 there, the plus 6 is not the coefficient. It's separate. It's just being added to it. What is the coefficient of x, even though it's not written there? 1. Exactly. Yeah, it's a 1 in front of it. Don't say it's a 0 in front of it, because then you're saying you don't have any x's. You have 0 x's. If I just say this is a water bottle, you may not say this is 1 water bottle, but in truth, it is only 1 water bottle. So if you don't say otherwise, there's usually an implied 1 involved. With a square root, there's actually an implied 2 involved. And you can even say x here has an exponent, even though it's not written. If you don't write an exponent, it's implied to have an exponent of 1 as well. So just some interesting facts to keep in mind. Now, we've talked about the concept of order of operations. That was a big to-do in Chapter 5. Your homework probably makes a nice big deal out of it. Now, you had some homework that was due this previous Thursday. You have some new homework that is due this Thursday. So just keep that in mind. Keep that in mind. You got some homework. You also have your exam. When is your exam? This Thursday, isn't it? Now, here's the sad truth is that we have another exam the following Thursday. But then we get a nice little 2 weeks without, well, we go 2 weeks before the next exam. And again, that's just because the exam schedule had to work out real funky, because we have to do 2 whole classes this semester. And I didn't want to schedule an exam over spring break because I'm not evil. I believe we avoided scheduling an exam right when you get back from spring break as well. Again, I have no evil in my heart. I let all my evil go years ago when I was a failed skateboarder. I would get all my feelings, all my passion, all my emotion out while I skateboarded. I would injure myself a lot because I wasn't very good. And when I finally told myself that one day, I said, Josh, you're just not very good at skateboarding. You can't run away from the fact that the only talent you have in your entire life is math. You can't run away from that. You have to embrace it, Josh. And so that day, I let my evil go. A little bit of my happiness went with it, but that's okay. Nobody needs to be happy. You just kind of would like to be happy. You can get through life not being happy. It's okay. I'm just kidding. I'm very happy. And I'm happy because video games exist. And I love video games. I played a lot of Minecraft over the weekend. Am I a 31-year-old man playing Minecraft? Yes, and I've been playing it for a decade since it came out. And I will not be shamed. Well, you can shame me a little bit, and I probably will feel some shame over it, but I'm gonna have to roll with the punches, My nephew likes it. He's 6, so it gives me a moment to bond with him. and I show them all the cool stuff I've built in Minecraft. Anyways, so that's just me rambling. I like to ramble. You probably figured that out by now. Order of operations, once again, are going to be respected, even with algebraic expressions. It won't quite work. In theory, it works the way it should, but it may not work quite the way you think because of the fact that there's an unknown variable. It throws a little bit of a wrench into the mix if you're talking about variables and things. But order of operations are still going to be important to us in this. They're the exact same, PEMDAS. Do anything that's inside of parentheses first, especially the innermost possible set of parentheses. Do any exponents that you can. If the exponent is on your variable, you really can't do much about that. There's not a whole lot you can do because if you don't know what x is, you certainly don't know what x squared is or x to the fourth power or anything like that. Then you do multiplication and division. You treat it like it's one thing. You do them from left to right. Then you do addition or subtraction. You do them left from right at the end. But the truth is, you're probably still going to end up with an expression that has a variable in it because you still don't know what the value of that variable is. It's not until you start to actually solve equations that you can really talk about that. So in this case, here's what they're doing. You say we have 7 plus 5 times x minus 4 in parentheses, and then it's cubed. X minus 4 is being cubed here. And it says 4x equals 6. So we're going to plug a 6 in for x. We are then going to respect order of operations. So this one's kind of a bait and switch because there's not really a variable involved anymore. We're plugging a 6 in for it, and it's goodbye yellow brick road to the variable. So see if we can follow on. Here's the original expression. We're popping a 6 right in there for x, and now we follow order of operations. We do what's inside parentheses first. Now, normally we wouldn't do 6 minus 4 because that's like at the tail end of it, but since it's in parentheses, it gets first dibs in our hearts. So we do 6 minus 4, which will give you 2. Now, everything else is still around it in its original place. 7 plus 5 times 2 to the third power. You're tempted to do 5 times 2 first, which would give you 10, and then do 10 to the third. But no, remember your order of operations. After you take care of anything inside parentheses, then you take care of any exponents. And that third power, excuse me, that third power is only going to the 2. So we need to do 2 to the third right away. 2 to the third, you're multiplying 2 to itself 3 total times. So you're doing 2 times 2, which is 4. Now we've done it twice. You go one more time. 4 times 2 is 8. Very good. So you're going to end up with 8. 2 cubed is 8. And then 5 times 8, you would do next, even though it's not first here, addition is, but we do multiplication and division before we do any addition. You get 40, and then you finally do the 7 plus 40, and you get 47. So not so bad. So this one was, again, it was a bait and switch because there was a variable, but all we were really doing is putting a number in for the variable and calling it a day. Now, just like I told you, you probably want to memorize the first so many squares. 1 squared is 1, 2 squared is 4, 3 squared, 3 times 3 is 9, 4 squared, 4 times 4 is 16. You probably, it'll be good measure, if you know your 12 by 12 multiplication table, you automatically know the first 12 squares. You can go all the way up to 12 squared. It probably wouldn't hurt to go all the way up to 20 squared and memorize that. 13 squared, 14 squared, 15 squared, and so on. It probably wouldn't hurt, in my humble opinion. So you probably want to know, you probably should memorize the first 20 squares. Something like that. You should probably also memorize the first 10 cubes. So the first 10 numbers cubed. 1 cubed, 2 cubed, 3 cubed. 1 to the third is 1 times 1 times 1, which is just 1. 2 to the third is 2 times 2 times 2, which ends up being 8. 3 cubed, don't do 3 times 3. Remember, taking an exponent is not multiplying. It's not doing 3 times 3. It's doing 3 multiplied to itself 3 total times, which ends up being 27. 4 cubed ends up being 64. 5 cubed ends up being 125. You probably should memorize the first 10 cubes. 6 cubed is 216. 7 cubed is 343. 8 cubed is 12, excuse me. 9 cubed is 729. 10 cubed is 1,000, so on. Probably wouldn't hurt, in my humble opinion, to memorize those first 10 cubes. Probably wouldn't hurt. Back to it. So now we talked about algebraic expressions. An expression doesn't have an equal sign. An expression is just a single statement, if you will, involving algebraic things like variables and numbers, addition, subtraction, multiplication, division, any exponents, roots. It's only when you put an equal sign to it and you try to set one expression equal to another expression. That's what creates an equation. And suddenly, when you have an equation, your mind is immediately like, I probably need to solve that equation. I probably need to solve that equation. Let's pause real quick. So like we're saying, an equation is a lot more than just a single expression. It's usually 2 expressions on opposite sides of an equal sign. Usually, you're trying to solve for a variable. If you can, if that's within your grasp. And then a formula is just an expression that relates, or it's an equation rather, that relates two or more variables together. You have the formula for volume. Volume of a simple rectangular prism, a box, is just base or length times width times height, if you will. You can talk about mathematical modeling. You can even use this expression here, W, which represents the number of calories needed per day by women in a certain age group. So if you're in the age range of 4 to 8, women need about 1,500, so children need about 1,500 calories a day, as do men if they're in moderately active lifestyles. But as you can see, as we get older, men tend to just need more calories. The truth is, on average, men are larger than women. I don't think that's a surprise to anyone. And so the larger you are, the more calories you need to consume in order to have a reasonable amount of energy. So we can express this where we use the error variable x to represent the age group. So this would be perhaps age group number 1. Age group number 2, you can plug in that value in for x. Now, you can't do these computations perhaps without a calculator. You could, but you'll be at it for quite a while, and it's usually just not worth it. But it's just interesting to know. So 19 to 30-year-olds, that's group 4 on that chart. So if you plug a 4 in for x into this formula, yada, 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 the formula indicates that for women in the 19 to 30 age group, they need about 2,078 calories a day. So that's interesting to know. course, there's a whole lot of other factors. That's just kind of an average. That's what the average perhaps would need. But there's all kinds of other factors. There's doctors who want you to eat more calories. There's doctors who want you to eat less calories depending on your situation. So this is not a, I must eat exactly 2,078 calories a day. That's just an average. Now we can get into the vocabulary of algebraic expressions. A single term. This is actually kind of important here when we get to solving equations. A single term is something that is separated from any other term by addition or subtraction. By addition or subtraction. So here you have 7x minus 9y minus 3. Because of these minus signs, that means 7x is itself a term. 9y is itself a term. 3 is also a term. The coefficient of the x is 7. It's the number in front. It's telling you how many of those x's there are. And really, it's saying that it's 7 times x. It's saying 7x. The coefficient of y is technically negative 9, is what we'd say. We'd say it's negative 9 is the coefficient. All of that. And then you'd call the last thing a constant. It's still sometimes considered a coefficient on its own, but it's a number without a country. It doesn't have an x or y variable, doesn't have a variable at all that it is attached to. It stands on its own, like Green Day. So we can talk about different terms. Combining like terms, that's the process of taking two things that have the exact same variable factors. Meaning, not only do they have the same variables, period, but the variables have the same powers on them. In this case, if you just have 7x, that's just an x to the first power. And so that would be a like term with a 3x, because while they have different coefficients, which is fine, their variable structure is exactly the same. That's what counts. And then anytime you're talking about a factor, you're just talking about things that are being multiplied together. The factors are the basic things that are being multiplied. So we got all kinds of wonderful terms, vocabulary throwing around. We probably really need to make sure we're clear on this vocabulary. And by probably, I'm just going to say we need to make sure we're clear on this vocabulary so we're all talking about the same thing, and it can help us avoid a lot of confusion later on. And so it turns out that the properties of real numbers, all the properties that we have already investigated, still apply whenever you're talking about variables. In fact, you can almost argue that the whole point of some of these properties are to give us a good guide, a set of guidelines when we're dealing with variables. And what are all the things we can do to manipulate variables, and how can we handle those things? So that's kind of some good news that's going on there. Again, there is a distributive property, and it doesn't matter. Remember, a variable is just meant to represent a number. We're not going to get into weird things where variables represent something else. We're just saying a variable represents a number. So anything you're allowed to do to a number, you're allowed to do to a variable all the same. Now, you may not be allowed to actually combine it. You can't do x plus 7 until you know what x actually is. So you just have to leave it as x plus 7. But the idea is it's still a number, so you can still manipulate it like it was a number. And so if you wanted, you could say I have 5 times, in parentheses, 3x minus 7. And then outside of the parentheses, I'm subtracting 6x. Okay, distribute that 5. Distribute that 5. You got to do 5 times 3x minus, because there's a minus sign here, 5 times 7. To do 5 times 3x, you can't multiply anything to the x just yet. You're not going to get anything different. All you can do is multiply the 5 and the 3 together, which will give you 15x. Minus, well, 5 times 7 is 35. So it becomes 15x minus 35 minus 6x. And now, if you can combine like terms in an expression, you pretty much always should, unless there's some really special thing you're doing. And here, I've got 15x, I've got minus 35 separately, but I've got minus 6x. I can tell the 15 and the negative 6x are like terms with each other. So group them together. In other words, do the actual combining. 15 minus 6x will give you 9x's. You have 35. It's not a like term with anything because there's no other constants on the board. So that just becomes 9x minus 35. We're going to need to do a lot of these kinds of things whenever we're solving equations. We're going to be running into that like no one's business. Anyone have any questions, either here or in the Zoomosphere? We're good. Our exam goes up to and including chapter 6.1 here, or section 6.1, which we just finished today. So unfortunately, we do have to spend the next 2 days lecturing over material that's going to be on the next exam. And again, that's just because sometimes the schedule, it doesn't always work out perfectly. So don't go nowhere.